So I am just a student doing his masters in a theoretical physics institute, and I just wish one day I become a particle physicist. So I just will try to make make discussion videos uh, in physics in general, but mostly I will be studying group theory and learning it and talking about it in these videos, and hoping I do it from scratch. From scratch, in a sense, only group theory from scratch. Whoever is watching is, I assume he knows some quantum mechanics, bachelor's level quantum mechanics and things. And so, yeah, that's it. So let's do group theory. So group theory is really important for particle physics, as far as I heard from people around me. Really, I don't know anything much personally. Me myself, I'm just a student, but I'm trying to learn, and I think if I learn while explaining, I might learn better. So this is just an attempt to develop. So in particle physics, group theory is very important. Apparently, people said that to me, and the reason group theory is important is whenever you have a symmetry, you get group. What that means is, as far as I know, if you have some system, any system, I will use this symbol for that, some wave function of some system, and you transform it, and when you transform this system with some operator, and after transforming, this wave function might get changed. I don't know, other wave function I might get, but if there is some property of this wave function, some property, I don't know, energy, momentum, position, something from of this system which is still conserved after applying this t, I will say that that quantity, let me call that quantity alpha. I don't know, that quantity alpha is invariant under t transformation. Let's say operator. Okay, operator. Okay, this is already going nuts. So let's first study group theory in mathematical point of view. What is group theory? Suppose you have uh, suppose you have things things in a, what do we say, a set of things. You have, let's say, a star, and let's say you have a moon, and you have some, I don't know, square, a triangle, uh, and let's add a circle, and with all this, let's say you also have a point. I will tell what this point does. So the thing is, I will define some kind of relationship between all these things which are inside this, let's make this boundary blue color boundary. Let me add another color. So now let me say that when I take this star, and combine it with the moon, let's say I take the star and somehow combine it, combining it, I will just use this with the moon. First I took the star and moon, and I got, let's say, a triangle. I don't know, I'm just making some rules. And let's say I took a square, I combined it with a circle and got a moon. So I can make these rules, right? And suppose outside this boundary I have some other thing. Let's say I have a pentagon. So the thing is, suppose I found that when I combine a moon and a circle, I got a pentagon. When the moment I find that this thing is not a group, so what I mean is, whenever I combine anything in these any two objects, any two objects inside this boundary, the result I should get should also be inside this boundary. If it goes outside, then it's not a group. Everything should be closed inside a boundary. So this already is very complicated. I don't know why I like complicating things. And if you survive 5 minutes of this video, wow, you have some hell of a patience. I will try to be let's try to be more neat. Okay, I will be a little more structured now. Suppose if you have a set and you have elements inside it, let's say let me denote the elements by x1, x2 up to you have n elements inside it, and you can also have infinite elements inside, but right now let us just consider finite elements. This set, if it follows some certain rules, then this set will be a group. And also um, just having a set is not efficient. On this set I have to define some operation, let's say the star, and this star is called binary operation. Basically I just take any two random elements and combine them and see what happens. That's what a binary operation does. Binary operation. And also order matters in binary operation. What element you're taking first and what second to combine matters. So now this set on which some binary operation is defined will be considered a group if any two elements I take from this set, let's say I took some xi from this set and also some other element, let's say xj from this set, I combine them and it still belongs to the set. If whatever the result is, I don't know, let's say I got some xi, I mixed xi with xj, I combined them and I got some xk. If this thing is also belonging to this set S inside whatever element I take of this inside this set, I don't care what two elements I'm taking inside this, every time I combine I should end up with the same set. If this is being satisfied, if this thing is happening, then one of the criteria for this set to be group is satisfied. I still can't conclude it as a group, but uh, I'm just sure that okay, there is one property which this set is following. So I have to check some more properties to confirm that it is a group. So first property is closure. This property is called closure property. You take any two elements, combine them together and see what the result is, and if it is still inside the set, it is following the closure property. So the next property is, let us come back. So this is done. Okay, remember I just wrote some kind of dot here. So the idea of the dot was, doesn't matter what I use to combine it with the dot. Let's say I combined a star with the dot. If I combine a star with the dot, I will get a star back. If I combine a moon with a dot, I will get a moon back. Basically this star is a neutral, this dot is kind of a neutral thing. Doesn't matter what you combine it with or what it combines with, you always get whatever you used to combine with the star. So that's what that thing does. So basically any element I take from the set and I combine it with that certain element, let me call it E, that it is very special, so I will just denote it as E. there is only always one of that element. I can't have more than one element, and it belongs to this. So this will automatically, this thing will give me the same element back. And the thing is, the element, I don't know how this works exactly, but when you combine it, it doesn't matter whether you first take this and combine it with T, you still get back the same thing, or you take this first, I mean you take this first and combine it, you still get the same thing, same exact same thing, same, these two are same. And now so this special thing E, this special thing E, uh, we term it as identity. An element in the set with which no matter what you operate doesn't change the thing you operated with. So the next property is identity property. And I am saying again, everything I am telling is already written in a lot of good books. You can go and refer them, because anyway I don't think I am sufficient in whatever I'm telling you. I don't feel confident myself. So um, so the third property is, so okay, the same element, the special identity which we used in the previous example, I mean in the previous property, it has another nice thing. So doesn't matter what element from the set you take, if I can always guarantee that there is some other element from this same set, and yeah, this may or may not be equal to j, it doesn't matter, sometimes it is, sometimes it is not. uh, Both cases are possible. uh, then then if so basically, if I take any element from the set, I can always guarantee that there is some other element such that if I operate it with my old set, with my old element, I will get identity back. And this new thing, which I can always guarantee must exist for all elements to give me identity, is called inverse. So let me represent the third property is inverse property. And finally, the fourth property, which confuses me the most, and I have my own name for it, but let me write the traditional name, and I will show what it is. It is called associative property. Or I would like to coin it as the chain property. Don't say chain rule, because that name is already taken by something else. So what is this chain property? So from that time I'm just taking two elements and combining together, but nobody is stopping me to take 3, 4, 5. So suppose I did something like this: x1, x2, x3. The thing is, binary operation only works in pairs first. You can't just take all of them together miraculously and tell the answer. uh, how measuring works in this binary operation is, you can only take this pair first, check what the answer is. Let's say it is I don't know, x1 star x2, let's say you got some y, then take this y and do it with this, basically y star x3. Or you are also free to do this. Let me write the same situation. You are also free to do this. You take this, find whatever the answer is, this time it may be z, and now do this. Yeah, and remember that you can't just take can't just do the take x1 and operate them together. This is not allowed. You have to you can only do with this with neighbors, local neighbors which are close together, which are beside each other. And if you do that, so basically the idea is if you have a like a chain of elements, I don't know, they can be as many as you like, and doesn't matter what pair you take first, then evaluate the answer, then take the other pair and keep evaluating. Doesn't matter what order you take. If you are always getting a nice unique one answer for this chain you took, and yeah, the order matters, you can't change the order. Once you have set the order, once you have said okay, this x1 comes before x2, x2 comes before x3, and once you set the order, and this x1 can be anything. Don't think that okay, I have to take some specific. It can be anything, it can be anything. Suppose you have abcd, or you have badc, it doesn't matter. This one will have its own answer, this one will have its own answer, that is a different issue. But my point is, doesn't matter what answer you have, if you what the answer is independent of what pairs you are evaluating first. Just read it from the book, if I am not able to explain properly. And so this all these four properties together make, if a set on which a binary operation is defined, they follow all these four properties, they are termed as a group. And we have some special groups where suppose I took x1 x2, the order matters, but I can't just simply take x2 x1. Generally this is not true for groups, it may or it may not be. So if the order doesn't matter, suppose I took first x1 and then x2 and flipped it, and then first took x2 and x1, if both of them are giving me the same answer, let's say some y, then this property where even the order doesn't matter. Before we were like okay, brackets, where we are putting brackets doesn't matter. Now we are like okay, even the order doesn't matter. If the order doesn't matter, which element comes first to be operated, at the end of the day, if you have the same elements which are being operated, then and the final result is the same, then that property is called commutative property. And we have another name for and if a group along which if a group which must obviously have these four properties, only then it is a group. But along with that property, those properties, if it has this extra property, that group is called abelian group. And I don't know what does abelian mean. Let me just check what abelian means in. So abelian, okay, abelian has no intrinsic meaning like other words have. I think it is some mathematician's name who is Abel, and he did some stuff in this group theory. So we coined the term abelian group for that particular property. It is there is nothing intrinsic about the word itself. So uh, let's continue. So all this is done. So so this is all the basic rule of group theory. Now I am more interested in what all physics can I do with this laws, this simple ideas. We have these four rules, and then sometimes you can have that one extra rule, the fifth rule. But generally you have the four rules. Four rules must be satisfied. Fifth one is a choice. It may or it may not be satisfied. When you have these rules, what all can you do with it? So yeah, these are highly abstract things, which are highly general. Highly general. It works on everything. Anything which satisfies these things, it will work on it. And this group theory is a theory in itself, very big. It doesn't even care about the physics. It is just there. You can just use it to anything. But we are more interested in the physics part. I will take some book. So there is this book here, which which I am which one of my friends recommended, and I'm just seeing it how it is, and so apparently the thing about group theory I found here is, let me see that sentence where it is. Hmm. Come on, come on, come on. I just don't know where it is, which I want to show you. So here is the sentence which interested me in group theory as well. This was so let me highlight that sentence. This is the one. In the 1950s, uh, particle physicists raced each other to find group with 8-dimensional irreducible representation. So basically, they were just solving an algebra problem. They were finding a group which satisfy these properties to predict a particle. And if not a particle, I don't know, something which was very interesting, and just got them, which might even give them the Nobel Prize. So that's crazy enough, I feel. And I just want to read it, so let's go and see what more can we do with all this. Let's continue, let's keep going. So I want to understand this. Let's understand this Scher's lemma, what exactly this says. I don't know what this is, so let me write that down. We have Scher's lemma. I don't know what this is, but it sounds important, and so let's try to understand it. So let me first Google it first, what this Scher's lemma is. I also have AI with me, so I can also ask it. If you have two irreducible representations of a group, any linear map intertwiner between them that commutes with the group action is either a zero map or an isomorphism. Damn. Okay, those are some heavy words, and I don't know where I am going with these words. I just jumped in. Just look at these words. I mean, I don't know what these are. And then there is commutes with the group action. Okay, group action, maybe they are telling the operator which does operate on the elements of the group, and no, operator doesn't operate on the elements of the group. Operator is something. Okay, let us come back on that later. So zero map, what is a zero map? Even I don't know that. Or an isomorphism. I think isomorphism I'm kind of familiar with, I guess, but other than that, these heavy words, no idea. Irreducible representations, blah 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 blah. We have to go through this. Yeah. And so what more do we have? The different irreducible representation statement. Let V and W be two irreducible representations of a group. If we go, so they define some linear mapping. and there is a composition. So there is a composition, there is some rule for the mapping, and okay, okay, we are okay. This is going crazier. Okay, oh my god, what is Scher's lemma? Let me see here. Hmm, I don't know what is happening exactly. I okay. Scher's lemma. Let me first recall what all I know. Look, you have an Hamiltonian, and this Hamiltonian, okay, and if we talk in matrix representation, this Hamiltonian is a matrix. When you act on a vector, and if this vector is the eigenvector of this Hamiltonian, then this Hamiltonian will split the vector out with some energy, and this energy is the eigenvalue of this eigenvector. That's for sure. And the thing is, this Hamiltonian will have numbers inside them, a lot of numbers. Let's say this is some n dimensional Hamiltonian, I mean n cross n matrix. So you have an interest in this matrix. You have an interest in this matrix. Here an interest n rows, n columns. And this matrix might get very complicated. You might need to play around with this matrix. Who knows, you have to, if you want to cube this matrix, square this, go nuts with this. You may not prefer to do it because it might be very complicated, but I can always decompose this matrix into three more fundamental matrices, where one of the matrix is a diagonal matrix which has all of its eigenvalues, and these two matrices will be eigen will be just matrices of the eigenvectors. Yeah, let's say this one is inverse of this one, and so here we are, this is what it will be. I can always decompose the Hamiltonian into three matrices, where U is a unitary matrix, this is a Hermitian conjugate of U, and finally this is a diagonal matrix. The nice thing about diagonal matrices is, I mean, the nice thing about this whole decomposition itself is, suppose you want to cube H, suppose you want to tell how much H cube is. Basically, you have to multiply Hamiltonian 3 times with itself, but you don't need to do it if you nicely decompose it. What happens is, all you have to do is to just uh, uh, multiply the diagonal 3 times with itself and just sandwich it between these u's. You don't need to do these 3 times, and you can easily compute d cube, because inside the d you just have the diagonal elements, and all the elements are zeros. They are just 0 0 0 everywhere, and when you cube this, you just have to cube the eigenvalues, and 0 just remains 0, and everything is still 0. So it just makes operations very easier. And I think this is what he means by irreducible basis. Like, I don't think you can go more simple than this. I mean, this is the most simple representation you can have for any matrix. Any matrix you give me, I will decompose this into this. Nothing can get more simple as far as I know. This is the best I know. There is nothing more simple, more fundamental than just decomposing matrix, just and doing this decomposing a matrix like this is called diagonalization. Diagonalization. Okay, uh, I messed up the spelling. So why do we want? So what is this book telling me? Okay, let me just see what it's saying. So I'm reading this paragraph. Let's see. Hmm. Degeneracy in the energy spectrum due to rotational symmetry cannot change. Okay, I think I need specific examples for this. If not, I won't be able to understand. That's how my brain works. I really suck in this. Okay, let me consider this one. What is telling? Suppose you have a particle in 1D. You have 1D. This is a one dimensional line. And the Hamiltonian which describes the particle is this. Let's say there is some potential in this line. So I can describe the equation of this particle in one dimensional motion like this. And now and this will be of course a function of position, a function in space. So no time dependence will be considered now. And so if this is the case, if this equation is true, let's say at all instants of time, if this is true at all instants of time, then what does it I have to rate it? Okay, so he and I have a potential which is symmetric by reflection. So basically, the potential uh, does does not change when I reflect the potential. So basically, the potential is something like this. Some examples of the potential: you can have a potential like this, a Gaussian potential. I don't know. I'm not able to draw this well. You can have a potential like this for an harmonic oscillator. You can have a potential. Let me make something more. I don't know, 1 by x square potential. This is also symmetric. If you have potentials like this, the thing is, if I physically try to think about this, doesn't matter if the particle is standing here or here, he won't be able to tell the difference. Is he seeing from the right or the left? these two things just look exactly the same. There is no way he can tell apart. It was me who just labeled this axis as plus minus. Labeling, physics doesn't depend on the labeling. Physics is physics, and this potential is symmetric by reflection, because if I just flip this potential which I have, I won't I will never be able to tell if I even flipped it at the first place. If I have some dementia, no, nobody can tell it. So if this potential is symmetric, okay, I lost it. I have to come back tomorrow. I will come back tomorrow. I don't know what all this is telling, but okay, that's all for now. Thank you. Oh man.